Everybody, this is Professor Jeff Wilkerson at Luther College with a quick introduction to our third experiment of the year in Classical Physics 2, Physics 182. And this is going to be a quick 1 week experiment. We don't typically do 1 week experiments. Two is the minimum. 3 and 4 weeks is much more common as we dig in and really try to understand the equipment and try to understand the system and try to think about how we're going to set something up. Because we extended the previous experiment 1 week to get a little bit better data and to think about what we were doing a little bit more, that cut in, and we decided we were just going to have 1 week, and we're going to fill this 1 week with looking at a device called a spectrometer. And this will be our first chance to look at wave optics. We've been looking at ray optics, and so now we're going to actually look at wave optics and interference from wave optics just a tiny little bit. One of the learning goals that we have for this experiment, probably the primary learning goal for this experiment, is to think about how we assess instrumentation. So we're putting a new instrument in front of you, this red tide spectrometer, and I want you to look at this and to think, how am I going to assess this piece of equipment? This is a skill that you'll carry with you forever as you go setting to setting to setting, is to say you're confronted with a new experimental apparatus, you're confronted with a new device, you're confronted with a new piece of software, you're confronted with all kinds of different things like this. You don't trust it. You don't just blindly take the data that comes from it and say, yeah, it's great data, or whatever the situation is. You gotta really assess that apparatus or that software or whatever it is you're working with, and you've got to make sure you understand it inside and out. And so this is the very first step in moving in that direction. So I'd call that our primary learning goal for this activity. But also we'll think a little bit about about interference of waves here, which we haven't done at all. And it'll be your chance to see a spectrum. So you should not get through an introductory sequence in physics without seeing the spectrum of something. A spectrum, it really is just intensity as a function of wavelength. So you can make a spectrum as a graph like this and say, how bright is the light as a function of wavelength? And what we're going to look at here is a line spectrum, so that this graph actually looks like this. You're going to see it as a picture. You're going to see it as bright lines that look like that. But if you think about translating those bright lines into graphical space, that's what your graph would look something like that. And really what we're about here today, we don't know where those lines are coming from. This is a classical physics course. We're not thinking about line spectra. We're not thinking about transitions in atoms. That's many of you have had chemistry. You've had these things before. You know where those lines come from. But that's not our goal. We're not open in that. We will return to that in the third semester next fall, and we'll use these red tide spectrometers again, and we will use these to look at lines and to think about the sources of those lines and to really better understand what's going on atomically in these systems. But that's not us here today at all. We're just looking at the instrumentation, and really what we're interested in is how wide are those lines and why are they that width? Okay, we want to know how wide the lines that come out of here are, and what it is that's causing those lines. Is it an inherent limitation of the instrumentation, what we would call resolution? Is it the resolution of the spectrometer, or is it something else that's causing those line widths? Do the line widths vary from line to line to line to line to line? In which case, it's probably not inherent in the instrument unless they vary in a very specific way. So, for example, they might vary with wavelength, and if they vary in a uniform way with wavelength, you can imagine that being a property of the instrumentation. We're just going to try. We got 1 week. We got 2 hours to go after this. That's not very much time to dig into a new piece of equipment and really understand it. It takes usually a lifetime, but that's another story. So we're going to go after this, and we're going to try to figure this thing out. And so this is what we're looking at. What the red tide spectrometer, we'll roll back to this in just a couple of minutes. What the red tide spectrometer has is a diffraction grating in there. And that diffraction grating has what is effectively a bunch of little slits. So often we will do at this point what we were going to do before we cut into this week's experiment is we were going to do a double slit experiment where we have 2 slits, and light will travel, light that's in phase. So if you got light that looks like that, and you got another wave of light that looks like this, we say those are in phase. They reach their peaks at the same time. They reach their troughs at the same time. So there's no phase factor between those waves. I don't remember how much waves you got during, I know we had to cut it back just a little bit, so I don't remember exactly what you saw during Physics 181 in the fall. But this is there's a phase. We'll get to this. We're going to do light waves at the end of the term here in the classroom portion of the class. So we'll get back to this, and this is the only part of light that we will do other than in the lab. But so we'll talk about the phase factor here. But these things are in phase if they line up like this. They're out of phase if they don't line up. They're completely out of phase. We'd say pi over 2, 90 degrees out of phase. So they're absolutely out of phase at this point, and they line up. If you take this wave and you add it to this wave, they cancel each other out. The trough cancels the peak cancels the trough, and you get that. It's not a wave at all, okay? And so in light, that would be a dark spot. If you have two light waves that are in phase like this, where the troughs line up with the troughs, troughs line up with the troughs, and the peaks line up with the peaks, then they're going to be what we call constructive. Destructive interference, constructive interference, often someplace in between. Partially constructive, some parts of the wave line up, some parts of the wave don't line up, and so you get something in between right here. But if they're completely in phase or completely out of phase, you get full constructive interference, full destructive interference, bright, as bright as the light can be. These two things adding up, as dim as the light can be. The intensity of the light is, for our purposes here, proportional to the amplitude squared. So it's the bigger the amplitude, the brighter the light. So if these two things are adding up, you just get a bigger amplitude wave, and you square that amplitude, and that's going to give you your intensity. If these things are, there's some problems with that interpretation, but not for what we're doing right now. And so now there's no amplitude, there's no light. So you see dark spots. With the two slits, you can imagine if these two lights go, if the light coming from these two slits is in phase, which it would be from our laser sources, okay? Would not be from most labs, but it would be from our laser sources. If this is in phase, then you can look at a spot on the screen, and the light had a travel distance that was longer from this path over here, from this slit, which just slides this. They started in phase, and you slide it a little bit, one wavelength. If you slide it one wavelength, then you get a bright spot. If you slide it half a wavelength, then you get a dark spot. There's a half a wavelength, there's a full wavelength. And so you go from bright spots to dark spots because that extra path length right there has to be, if L, the extra path length, is equal to n lambda, then where n is an integer, then you get a bright spot. If it's n plus a half lambda, you get a dark spot. So if you have light shining through a double slit like this, then you will see alternating bright and dark spots, because as you move along this screen, that extra path length gets longer and shorter, longer and shorter. And so it's varying what that extra path length is. And so you get this path length interference, alternating constructive and destructive interference. And so this is the experiment we had set up to do this week, last week and this week. But we replaced last week with the continuation of our search for chromatic aberration. So we decided to go with the spectrometer this week because I wasn't sure we could get as much of this as we wanted to get done in a single week. We could have done some of it for sure. But we decided to look at the spectrometer because it's a great experiment too. What the spectrometer does is it takes this grating and it rules what is effectively a whole bunch of these little slits. It's not actual slits in a dark opaque apparatus. It's ruled. It's glass with lines etched into that glass. But those look like this. When you add a whole bunch of these slits up, you get a whole bunch of different interference things going on like this, and you can then get a different wavelengths will be constructive at different spaces across here. And the more slits that you have here, lines per inch, so we would measure the grating in lines per millimeter or lines per inch or lines per fathom if you want, I don't know. And so we would measure the number of lines etched in here per some distance. And the more the number of lines are, the greater the resolution, the finer the spread in wavelengths, right? If you don't have, if you have one line, no lines, basically, if you have one line, then all the light, there's no resolution at all. You just see one big bright spot from your lamp. And so as you start to add lines, you get the light, you start to get more and more of the rainbow, and you get brighter. You know, the blue would be brighter, and then the green, and then the red would be brighter out in here. And as you get more and more and more lines, you narrow those different regions down, and you get tighter, 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 and you can start to see these individual lines appear. So what you're going to do is you're going to take your red tide spectrometer, and you're going to point it at a helium lamp. Okay? The helium lamp has a lot of different lines in it, and it's going to be confusing, but that's part of what the experiment is about, is to say you're going to look at the helium lamp, and you're going to see a spectrum that looks something like this. And you're going to ask, I don't know if you used Logger Pro in the fall, typically you would have. We're going to use Logger Pro to control our experiments for most of the rest of the term. So if you haven't done that, we'll spend the first 10 minutes getting everybody up to speed on Logger Pro when we get into the lab here. And making sure we know how we want to store that data and how we want to handle that data. So we're gonna look at the lamp. So here's the lamp. You got a tube that looks something like this, and this tube's filled with helium gas, and it emits a pink light. And that pink light, you're gonna hold your fiber. If you hold the fiber right up next to it, what's gonna happen is you're gonna saturate the bright lines. And so the bright lines on this graph, so the software is going to give you a graph like this. You're going to look at it and say, oh, that's nice. You're going to see the graph that looks like this. And you're going to see all those lines. And you'll see there's a bunch of little faint lines down here and a bunch of big bright lines. If you want to see the faint lines, you got to get this fiber right up next to the lamp. But what that's going to do is it's going to turn these bright lines into flat tops. It's going to saturate the detector. So there's a detector of light within, in addition to this grating, you got to have something that's detecting the light. And that detector of light can get too much light and it saturates and you see a flat top across here. Okay, but that's okay. You still extract the data and you use that data extraction just for these fainter lines, because as those get flat topped, these get bigger and bigger and bigger and bigger. And so you want something in here. You want to see your line somewhere in the middle of the range from 0 to the maximum value that's up here. And I forget what that maximum value is, but you'll see it very clearly where it starts to flat top across there. It starts to saturate your detector. And so then you'll pull the fiber away and hold it at a different angle, and you can get these brighter lines that aren't saturated, and you can use that extraction for the brighter lines. You'll probably have to do at least 3 extractions, maybe 4. One really close that saturates a whole bunch of lines, but gets the really faintest lines in there, and then one in between there, and then one pretty far away where you're just looking at the brightest lines that are in the spectrum. And then you'll have all of these lines to assess. If you have a line that looks like this, what you do when you extract the data is regraph it in MATLAB or Kaleidograph and fit it with a Gaussian. Okay? And we're going to define that line width as sigma of that Gaussian. So you're going to fit it to the sigma there. And one of the things, is sigma the same for every line that's in there? Is sigma over mu the same for every line? If sigma is delta lambda, mu is lambda. Okay, and so the mean is going to tell you the best fit wavelength for that line, and the standard deviation is going to give you some estimate of the width of that line. And so we're going to look at sigma, which is just delta lambda, and ask how delta lambda varies from line to line. And we're going to look at sigma over mu to ask how delta lambda over lambda varies from line to line. And maybe your assessment, your job is to assess this and make the graphs and to look at these things. And maybe your assessment suggests you want to look at something different. Maybe you want to look at sigma over lambda squared, I don't know, or something along those lines, and to get a different sense of how does this line look the same as this line way out here. Do the lines that are close to the purple end of the spectrum or the red end of the spectrum, do they look like they're the same in terms of resolution, in terms of, this would be called resolution of the spectrometer. Is that a constant across there, or is it varying with wavelength, or is it just chaos? Is it just all over the place? In which case it suggests it's probably something to do with the lamp and not something to do with your spectrometer, and we want to explore it further. Now, you got a couple of complications here. One of the complications is that there's all these other little lines in here, and these lines are going to look like a mess down in here. And what you realize is you may have to fit more than one Gaussian. Cut this line out, and there may be 3 Gaussians in there, and you have to fit the sum of 3 Gaussians. Just write the code to do that. Write it right into the Kaleidograph formula box or right into MATLAB to fit 3 Gaussians, mu1, mu2, mu3, sigma 3, sigma 2, sigma 1. Okay, you might have to fit 5, or you might have to fit 9, or you might have to fit 2, or whatever in a given region. Or there may be a given region where it looks clean. But even if it looks clean, be aware that there might be 2 lines in there on top of each other. You can't tell there are 2 lines. Okay, so you've always got to be concerned about what's going on there. A lot of times you might see something that just looks like it has a shoulder like that. Probably a second line. It's probably 1 Gaussian, 2 Gaussians. Okay, and so you got to fit those 2 Gaussians in there like that. And so you got to be making all kinds of decisions and trying all kinds of different things with your fit. The data acquisition for this lab is going to be short. You're going to go bam, 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 and you're going to have the data from this lab. And then you're going to spend a lot of time messing around with it and trying to understand what's going on. As a final step to test this, whatever conclusions you're drawing about this spectrometer, about its resolution, about its performance, about whatever. So you're drawing these conclusions. The final step, take your spectrometer over and point it at the window and look at the sunlight. You don't have to look directly at the sun with the fiber, just look at the bright sky, and you will see, instead of bright lines, you will see a spectrum that has a bunch of dark lines on top of a background. That background is a black body background. We haven't talked much, a little bit about black bodies, but not much. And so you got all these dark lines on top of a bright spectrum. Extract that and fit these dark lines as negative going Gaussians. You can flip them over if you want to fit the Gaussians, but you got to subtract off this background and have this Gaussian riding on top of a background, which the Gaussian fit we have built into these things actually does have a background level built right into it. So we want to see this Gaussian, and does this line width look like this line width? Okay, if the line width so pick out 4 or 5 or 2 or 10 or whatever you can lines in the sun. You have a real problem in the sun because the sun is a type of star that we would say is line blanketed. So in the green region of the spectrum, there are so many lines, it's really hard to fit those lines. But if you can get out on the tails away from the green part of the spectrum, you can find individual lines to fit. Fit those lines and see, are they consistent with the fits that you got here? If the sun looks like the helium lamp in terms of lambda, delta lambda, or delta lambda over lambda, or whatever behavior, if its behavior in terms of resolution, in terms of quality of data is very similar to the helium lamp, that's at least a piece of evidence in support that delta lambda or delta lambda over lambda is inherent in the instrumentation, because the sun is very different from that helium lamp. And if you look at 2 sources that are very different and they give you the same kind of behavior, it tells you, hey, maybe our resolution is being limited by our instrumentation, and so it's the instrument that we're dealing with, that we're working with, that's doing that. So that's what you want to do, is you want to look at the sun, take the spectrum of the sun, compare it to this spectrum, and see what you can do. And then because it's a short week, it's a 1-week lab, it's a short lab, we're not going to do a full write-up. I don't want an introduction, I don't want a procedure, I don't want anything. I want your graphs, your analysis. I want a whole bunch of analysis graphs, and then a paragraph. I want you to write a good detailed paragraph discussing what you think you found, how you went about doing the fits, why you did the fits you did, and what the results were, what you think you learned about the performance of this instrument, about the resolution of this instrument. So that's what we're doing. That's what we got this week. We'll see everybody in lab, and hopefully it goes well. Have a good week, everybody.